Hello, let's continue our advanced Sudoku series with Tatooine Oasis by Philip Newman. So this is the seventh puzzle and last puzzle of chapter 3 of the Sudokult Gospel document. There are more chapters, don't worry, there's more puzzles. As always, I know what technique I'm looking for, but not where it is in this specific puzzle, although I have some ideas. And that way I'm able to explain the technique properly. And there is a link in the description if you'd like to try the puzzle yourself first, and I'm going to get started right now. So, based on what I know about this puzzle and about, in general, the Tatooine binary sunset type classic that Philip creates, I am going to skip straight to the set interpretation here. I'm not even going to do scanning. I am going to just go straight for set, and I'm going to see what I can get out of that, because I think that's going to be more fun. There is a way to do this more traditionally, using techniques that we've used during this chapter without using set, but I thought I would skip straight to set and show you the power. So the question is, where do we want to make this set? Well, I think the puzzle is kind of broadcasting that these sort of circular patterns are very important, along with kind of the additional circles that appear below them. Do you see that? And so I'm thinking these, when we have these highlighted, oops, I didn't mean to highlight that. There's kind of 3 columns of interest and 3 rows of interest that have a bunch of givens in them. Now, if you remember, when we draw a set, if you watched my video from last time at least, what we want to do is we want to try to hit as many givens as we can, and then eliminate as many empty cells as we can. So let's see what happens here. So I'm going to highlight these 3 columns. These 3 columns are going to capture, I think I'll do this column, not the other one. This column is what I meant. I'm going to do these 3 columns because what's nice about these 3 columns, let's make those green. They capture quite a few of the givens in our grid. And in addition to that, they line up in the rows, which means if I avoid using those rows, then those givens won't get canceled out by my row set. So I'm doing these 3 columns, and then the rows, I want to try to capture the remaining of these kind of circulars, organized digits. So I'm going to get this row, and this row. So we're doing a balanced set today. Let's do purple here. So I will go over what this means just in case you missed last video. But the way set works is set stands for set equivalence theory, and set stands for set equivalence theory, and then anyway, you get it. It's a recursive acronym. The equivalence is the important part. We're doing equivalent sets. So the green cells, now remember that these cells are both purple and green, but when we talk about the green cells, what digits are in the green cells? How can we describe that? Well, we know exactly what digits are in the green cells. We just don't know where they go. Partially. We know where some of them go. But it is 3 columns, and each column has the digits 1 to 9 exactly once each. So 3 columns has 1 to 9 3 times each. So if I were to take, I'm going to use the Scrabble bag example again. And in my left hand, if I have a Scrabble bag, and I have put in 1 of each of 1 to, or 3 of each of 1 to 9, of like number tiles into my Scrabble bag. I can jingle that around. I've got a total of 9 times 3. I have 27 tiles in there, 3 1s, 3 2s, 3 3s, etc. That is my green tiles. Now, what about purple? Well, purple is 3 rows. Purple is also 3 of each of 1 to 9. So I can have in my right hand a bag of purple tiles, 3 of each of 1 to 9. So I have 27 tiles in my left hand, and I have 27 tiles in my right hand, and they are the same. The green bag contains the same exact digits as the purple bag because they each contain 3 of each of 1 to 9. Now let's look at this cell here. This cell is in both purple and green. We don't know what digit it is. It might end up a 1. It might end up a 6. Not a 6. It might end up an 8, a 9. We don't know what it'll end up. But whatever that tile is, if I'm able to find it and remove it from both the green and purple, we know it's in the green and the purple because green and purple both contain this cell. Whatever number ends up in this cell, they contain it. I can remove it. And if I pull that out of both bags and I throw that out, both bags now have 26 tiles in each, and they are still the same 26 tiles as each other. I don't know if I've removed a 1 or an 8 or a 9, but what I do know is that I have removed the same from both. And so now I've lost track of exactly what digits are in both, but we know they're still the same. And I can do the same for all of these cells where they intersect. So all of these cells I've removed. And so what I know on my grid is that the green cells and the purple cells are still exactly the same digits as each other. However many ones are in green, that same number of ones are in purple. However many twos are in green, that many twos are in purple. Well, look at this. I've got, and we know they're equivalent. So I've got 2 sevens, right? I've got 3. Okay, let's start with this. I've got 3 5s in green. How many 5s have I accounted for in purple? Well, the answer is I haven't accounted for any in purple yet. So I need to place 3 5s somewhere into these cells. You may notice that this is a swordfish, right? So if I'm going to put a 5 into these cells, where am I going to put them? Is often the question to ask. So I could put a 5 in one of these two. I could put a 5 in these. And I could put a 5 here. So 5s are going to end up somewhere in here. Now, the important thing is if 5 ends up somewhere in purple, that means they don't end up in these intersections. That means I didn't remove any 5s from purple, so I couldn't have actually placed any 5s. I couldn't, because I didn't remove any 5s from green, I also didn't remove any 5s from purple. And so the ones I removed cannot be 5, right? What else can we say about green versus purple? So purple has 3 4s. So I didn't remove any 4s from purple, which means I didn't remove any 4s from green, right? So that means that these intersections also cannot have any 4s in them. Now we already kind of knew that because of these rows. So let's think a bit harder here. So I need to put 3 5s into purple. Let's actually count this up. Okay, so the next thing we can do is we can actually look at what we know is in purple and green, and we can try to pull out identical tiles that way. So for example, I've got 3 3s in purple. So let's go through each digit one at a time. Are there any 1s in green or purple? There are none. Okay, so that's an important thing to notice. There are no 1s that we know about in purple and no 1s that we know about in green. I guess that doesn't mean a whole lot yet. So let's keep going. 2s are only in purple. They are not in green. 3s are only in purple. They are not in green. 4s are only in purple. They are not in green. 5s are only in green. They're not in purple. 6s are only in green. They're not in purple. 7 of known spots, right? 7s are we only know about them in green. We don't know about them in purple. And then 8, we know about an 8 in both. So I can remove these 8s. Because I can remove an 8 from purple, I can remove an 8 from green, and they still have equivalent. So, but what this means is we can count. We have 1, 2, 3, 4, 5, 6, 7, 8 digits in purple that need to go somewhere in green because they're not already accounted for. Oh, sorry, I did miss a 2. So let's remove 2 2s. It doesn't matter which 2 we use. I mean, we got to remove the one from green, but it doesn't matter which purple we use because we're just doing a counting argument. So now I've got 1, 2, 3, 4, 5, 6, 7 placed digits in purple. And I need to put those into green somewhere because I've got a single 2 that needs to go in green. I don't have any 2s in green. I've got 3 3s that need to go in green. I don't have any of them in green yet. I've got 3 4s that need to go in green. I don't have them in green yet. So 1, 2, 3, 4, 5, 6, 7. How many open greens do I have? 1, 2, 3, 4, 5, 6, 7. I have 9 open greens. So it's not an exactly equivalent set here. It's possible that had I done some scanning, I may have actually found some more info. But I was hoping I could do this right from the start. So, and then I've got 1, 2, 3, 4, 5, 6, 7 in green that I need to place in purple. And I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 open in purple as well. So let's think about how we're going to do this. So I need to place. I think I might need to do some Sudoku in order to get more out of that. Unfortunately. I was hoping that that would just give us what we need here. Because there's 2 degrees of freedom in our set here. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. So I know I'm going to need. Green is going to need 3 3s and 3 4s. So each of these columns is going to need 3 and 4 in it. And then in addition to that, I need a singular 2. So, one thing we can say is that 3 and 4 can't go in any of these cells, because I'm going to need green to accept 3 3s and 3 4s. This is probably what our swordfish would have given us on 3s and 4s. And so if I were to put a 3 or 4 into any of these cells that I've highlighted here, these blue cells, they can't be 3 or 4, because if they were, then I wouldn't be able to fit 3 more 3s and 3 more 4s into green. So I don't care about these givens here. But what we can do is we can mark all of these as not 3, 4. So I can mark these as 1, 2, 5, 6, 7, 8, 9. And we could clean that up. Now let's look at the 5s and the 6s as well. The 5 in the actually, so I have 1, 2, I have 3 5s here. I have 2 7s and 2 6s. So the 5s are the important ones. I need to put 5s into purple, into these cells in purple. And because they line up in the columns, these cells actually cannot be 5. So let's deal with the let's deal with these cells first. 1 2 5, 1 2 6, 1 6, 1 7 8, 1 7 8, 1 2 7, 1 2 5 7, 2 6 8, 2 6 8, 1 5 6 7 8, 5 6 8, 1 2 7 8. So if I get rid of these blue cells, then what I can do is I can say, okay, I know that purple is going to need 3 5s in it. So, and those have to go in these cells, which can be covered by these 3 columns. So I'm going to need to not place 5 into any of these cells. None of these cells can be 5. So let's make those blue. We can remove 5 from here. We can remove 5 from here. And then the remaining of these cells are from 1, 2, 3, 4, 6, 7, 8, 9. So we'll clean that up now. 2, 6, 7, 8 can't go there. 2, 3, 7, 8 can't go there. 4, 6, 8 can't go there. 1, 2, 6, 8, 1, 3, 6, 7, 8. 1, 2, 4, 6, 7, 8. 1, 2, 7, 8. 1, 4, 6, 7, and 1, 3, 6, 7. Okay, is there anything else I can see about this? Okay, so here's another thing. I'm going to keep these blue because the purples are also going to need 2 6s in them, because there's 2 6s in green. But guess what? None of these can be 6 because there's a 6 in the column already. That means I need the 2 6s to go in these columns here, which means none of these blue cells can be 6 either. So let's, here, I'll just highlight them all, and then we'll double tap 6. So that'll add 6 and then remove 6 from them all. And then same with 7, I think. So we do have 2 7s in purple. Now, can any of, yeah, and so this last column here can't have 7s in them. So the 7s need to go here. So none of these blue cells can be 7. Double tap that, and now we get naked singles. We get the 9, we get the 2. These are not 9s. This is not 2 or 9. That's not 9. That's not 9. These aren't 9. Okay. Now, did I miss anything with the other blue? Because I didn't think about how that might be restricted. So let's talk about these again. What I have may be enough, but we'll see. We'll just highlight all these. And what happened here? Oh yeah, this one ended up not green. Oh yeah, I just want the 3 rows that are empty greens here. So what did I need? I needed 3 3s, I needed 3 4s, but I also needed a singular 2. Now that can't go here because there's already a 2 in blue. I think these could be 2, or these could be 2 though. We know we have exactly 1 2 in the, hold on, the greens though. It's the greens we care about 2s in. So let's get rid of any, okay, these greens can't be 2. I don't want to get rid of them, but these greens can't be 2. And these greens can't be 2. I don't know that I can actually do anything with that. Interesting. Okay, so I think that's it. I think that's what we get. So that has seeded our grid. I'll keep, I'm not going to keep the blue, but oops, I will keep the green and purple around, so we can continue to use that if we need to. So I got this 9, I got this 2. What can we do? I got to scan here. It's going to be harder to scan because of all the markings I've already done, but looking to see, let's see, 1, 3, 4. So this is a 1, 3, 4 triple. So this is going to be a triple as well. We've got 1, 2, 3, 4 accounted for. We need 5, 6, and 7. So that's not 6, that's not 7, that's not 5. So there's a 5, 6, 7 triple in, yeah, so we found, okay, so if I get rid of these from purple, I can get rid of these from purple. It doesn't matter which I pick. But the point is I found where 5, 6, 7 go in that green, so I can also remove them from the purple bag. Let's see. I wonder if I could have proven that they had to be there. I'm not sure. That would have been interesting to prove I had to have 5, 6, 7 there. So what do I have left in green? I've got 2 5s, a 6, and a 7 in green, which have to end up in here somewhere. So 2 5s, yeah, and then a 6 and a 7. So these can't be 6. So the 6 has to go in these, but we already kind of have shown that through our markings. All right, well, let's keep looking at Sudoku here. This 4 looks in here. This 4 looks down. That lets us put a 4 in one of these two. There are 2 4s in purple. We need 3 4s in green. It's not helpful. I got this 9, I got this 2. We got this triple here. Also this 5, 6, 7 triple. What's this doing for us? Threes look into this box. So 3's in one of these two. Let's see. This can't be 2, 3, 4, 5, 6, 7. So this is from 1, 8, 9 only. It's not a 9 either because of that 9. So this is only from 1, 8. It's not 2, 3, 4, 5, 6, 7. They're more like that. This is not 2, 3, 4, 5, 6, 7 either. So this is from 1, 8, 9. These 2 7s look into this box. That puts a 7 in one of these two. These 2 6s look into this box, putting a 6 in one of these two. These 5s look into this box, putting a 5 in one of these two. We got the 4s. 2 in this box. Yeah, okay, so we have a hidden 2 7 pair in this box because these 2 7s look in, and then also we have these 2 2s looking in. So this is a hidden 2 7 pair. Now, is there anything about purple having a 2 7 in it that's interesting? I can almost not put a 2 over here. See, how many 2s are already? So we already have a singular 2 in purple. Interesting. All right, so if that's a 2 7 pair, what's the remaining in this row? We need a 1. Oops. We need a 1. We have a 2, 3, 4. We need a 5, 6, and 9. Okay. Clean that up a bit. 1, 9. 2, 7, 5, 1, 5, 6, 9. Can this be a 6? I don't see why not. One thing we can think about is how many more 6s can we put in purple? Actually, we need a 6 in purple from the green, right? The green is telling us we need at least one more 6 in purple that go here. And these can't be 6, right? So 6 goes in one of these 3. I don't think I can say more than that. Yeah, we already did that, I guess. Just trying to think if this could be a 6, but I think it can. Okay, what else am I going to find here? 3, 6, 8, 9 here. This is 8, so this is 3, 6, or so it's not 6 either. So this is 3, 9 only. 2, 3, 4, 5, 6, 7. I'm seeing how many degrees of freedom we still have here. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Yeah, I still have two. I have two extra digits that are going to be the same in both, but that do go in both. Interesting. These two 2s are looking down. This 2 looks in. That places a 2 in green. That sounds important. That gives us this 9. Okay, so we're going to get some Sudoku from that. 2, 9. These aren't 9s. That's a 5, 6 pair there, so that's not a 6, leaving a 1, 9 pair. So we got a 2 in green, so we can eliminate these. We found that too. Okay. All right, what do we get from that? We got the 5, 6 pair. We got the 1, 9 pair. Almost have like a 2, 3, 4 going on here. Got this 9. What does that do? Did I get that 9 just now? I got this 2 for sure. I think I got the 2 and the 9. 9s in this box are here. 9s in this box are here. We have a 1, 5, 7 triple here, so this is a pair. We need a 3 and 4, and this can't be the 3. Nice. So that's a 4, that's a 3. That's a 9. Ooh, 9 is one of our bonus digits, I think. That's not a 9. This is not a 3. This ends up a 2. That's not a 2. That's not a 9. That's a 5, 6 pair. So what I want to do is I want to eliminate these 4s. I want to eliminate these 3s. Now, I got a 9 in green. That means I need a 9 in purple. So one of these ends up 9. That sounds important, right? Because this 9 tells us 9 doesn't go here. One of our bonus digits was a 9. We need a 9 in one of these two. And so this can't be a 9, and this can't be a 9. Now, can both of these be 9? It looks like it. Well, this 9 looks down, so 9's in one of these two. This 9 looks up. 9's in one of these two. Yeah, so one of these ended up 9. Got this 4. This is a 2, 8 pair, so these aren't 8s. So that makes that a 3, that a 4, that a 1, that a 9, that's a 1, that's not a 1. Okay. Oh, we get the 3 down here as well. We get the 4 up here. We get a deet deet doot on a 3, nice. 1, 2, 3, well, what's going on with this? We need to find an 8 somewhere, I guess. All right, how are we doing? So we know the 9's in one of these two. We got one of our bonus digits. We have one more bonus digit to find. Now, I do need 2 3s still in green. Okay. That's important. Okay, so green needs 2 3s in it, and this can't be a 3. So that means there's a 3 in one of these and a 3 in one of these. Kind of like an X-Wing. Is there anything that does? I don't think that does anything. Unfortunately, it doesn't. Okay. Let's look at this column. This column needs a 1. We have the 2. We need 3, 4, and then 6. Well, not 6. 8. So this can't be 3, 4, or 8. It sees the 3, 4, 8 in the box. So this is a 1. That cleans up the... Oh, and this sees 1, 3, and 4 now. So this is the 8. That's a 3. That's a 4. Nice. So I can eliminate a 3 and a 4 from these. Boop. That's 1 and 9. That places this 9. Okay, so now we found our 9s. Good. This is a 9 now. That's not an 8. Okay, so this is from 5, 6, 8. It's not a 5, so only 6, 8. What else do we have here? The rest of this row is, whoa, 6, 8, 9, it looks like. That's not an 8. That's not a 9. 6, 8 pair, 2, 7 pair. Okay. That's not a 3. That places the 3 here. Okay, so green needs a 3. It's right here. Yeah, this is the 3. Also for 3 for the column. All right. We need a 4 in green. I did that right? Yeah, I need a 4 in green. I still need 2 5s in purple, interestingly. So this is the only place for 5 in this column for purple, and we need to use both columns. So that's a 5, that's a 7, that's 6 and 7, that's 8, 5 and 6, that's 5 and 7. We get the 6 here, the 9, the 5 here. We got both of our 5s now. We get the 6 and the 8. That's not a 7. This is a 1 and a 5. That's not a 6. So what do we have left here? We know that we need a 4 somewhere in green. We need a 7. Okay, I need a 6 and a 7 in purple. Yeah, I'm not sure exactly. Let's just do Sudoku. At this point, it's Sudoku. That's not, I mean, at this point, it's just simple singles. That's a 1. This is a 7. That makes that 2 and 7. Okay, now purple has a 7. That's good. And so now we know, we still have our kind of degree of freedom, which is kind of funny. This is what for the row? Looks like it's, what is it? It's a 7. Okay. This is a pair. This is 6 and 8. Okay. And this is also 6 or 8, so it can't be the 8. So that's 6, that's 8. We found our 6s. And so now this is going to be a 4-8 pair. Might as well use it. So we get the 8 and the 4 here. That's 2 and 5. That's an 8. And we have finished our set. Yay. And we finished the puzzle. That's a 6. We get a 2 here and a 1 here, and we're done. We got the correct solution. All right. So that was a little bit of a weird use of set there, I think. But it came in handy throughout the whole solve. I'm wondering, had I scanned a bit more at the start, would I have found more from the set? Like, was it limited more? Or did we just end up with those 2 degrees of freedom? We still were able to reason about what the swordfish eliminations were, but we were able to kind of reason at them maybe a little bit more easily. And maybe we were able to use this a bit more during the solve, when normally we would have just had to, find more triples and pairs and things like that. So yeah, let me know how you felt about this solve. And of course, if you enjoyed this, why not leave a like, subscribe, and a kind comment below.